Today we're going to talk about the molar mass of a compound. Since compounds are made of elements and elements have molar masses, it stands to reason that we can have molar mass of a compound by just summing up the molar masses of the elements in the compound. Let's learn this by example. Let's take KClO3 and find what its molar mass is. Well, KClO3 has got 1 mole of potassium. I know this because there's no subscript there, and that implies that there's a 1. So I'm going to take 1 mole, the number of moles in a mole of KClO3, and multiply it by the molar mass of potassium. Potassium's molar mass is 39.102 grams per mole. Remember, you can get that off the periodic table. So the total mass of potassium in a mole of this compound is just 39.102 grams. For chlorine, again, there's a subscript 1 that's implied there because there's no written subscript. So I'm going to take 1 mole and multiply by the molar mass of chlorine, which is 35.453 grams per mole. So that just gives me a total mass of 35.453 grams of chlorine in 1 mole of KClO3. Oxygen. Well, the subscript 3 implies that a mole of KClO3 has 3 moles of oxygen in it. Oxygen is 15.999 grams per mole. And when I multiply this out, I get 47.997 grams. So 1 mole of KClO3 consists of these masses of individual elements. I'll add them up. When I do that, I get 122.550 grams per 1 mole of KClO3. There's my molar mass. Let's do another example for a molecular compound, H2SO4. I have hydrogen in here. The subscript of 2 means 2 moles of H. The molar mass of hydrogen is 1.008 grams per mole, so that means I'll have a total mass of 2.016 grams of hydrogen in 1 mole of H2SO4. Sulfur, subscript of 1 is implied here, so 1 mole times the molar mass of sulfur, which is 32.064 grams per mole. And that leaves me with grams of sulfur, and that'll just be 32.064. And then for oxygen, I have 4 moles of oxygen in 1 mole of H2SO4, and each mole of oxygen weighs 15.999 grams. So when I multiply these together, I get 63.996 grams of oxygen. So 1 mole of H2SO4 is the hydrogen plus the sulfur plus the oxygen all added up, and that comes out to 98.076 grams per mole of H2SO4. You try one. Stop the video and figure out the molar mass of calcium nitrate. Well, here's your answer. There's a subscript of 1 implied on calcium, so that means 1 mole times calcium's molar mass. Calcium's molar mass is 40.08 grams per mole, so that just gives me 40.08 grams of calcium. Nitrogen. Well, the parentheses around NO3 means that everything inside the bracket is doubled because there's a subscript 2 after it. So that means we have 2 moles of nitrogen here. Nitrogen's molar mass is 14.007 grams per mole off the periodic table. When I double 14.007, I get 28.014 grams. Oxygen. Well, there's a subscript of 3 inside the parentheses, so that means 3 O's for every nitrate. But there are 2 nitrates in this compound, so that gives me 6 moles of oxygen for every mole of calcium nitrate. Oxygen's molar mass is 15.999 grams per mole. When I multiply those together, I get 95.994 grams. So the mass of 1 mole of calcium nitrate is the sum of the calcium, the nitrogen, and the oxygen. When I add that all up, I get 164.09 grams per mole. Here's another example. Stop the video and try this, and I'll give you an answer in a little bit. Question is, what's the molar mass of calcium chloride? There's a subscript of 1 implied on the calcium, so for calcium that means I have 1 mole of calcium per mole of the compound. Calcium is 40.08 grams per mole, as we saw in the last example. So the total mass of calcium in our compound is 40.08 grams. Chlorine has a subscript of 2 implied. So 2 moles times the molar mass of chlorine, which is 35.453 grams per mole. So that gives a total of 70.906 grams of chlorine in the entire compound. So when I add these up, I will have 110.99 grams for every mole of calcium chloride. One more. What's the molar mass of magnesium phosphate? Stop the video, make a chemical formula, and then figure out the molar mass. Well, magnesium phosphate, I'm going to have to get this by charge swap. Magnesium's 2+ because it's in the second column. Phosphate's a polyatomic ion. Anything that ends in ate or ite is going to be polyatomic. And if I look it up, I find that it's PO4 with the 3- charge. So when I charge swap, here's what I get. Magnesium gets a 3. Phosphate, PO4, gets put in parentheses, and it gets a subscript of 2. So that means to find my molar mass, for magnesium, I'm going to have to take 3 times the molar mass of magnesium, which is 24.305 grams per mole. So it's 3 moles times that number. And that comes out to 72.915 grams of magnesium in a mole of the compound. For phosphorus, well, there's 1 P in every PO4, but there are 2 PO4s. So that means a total of 2 moles of phosphorus in a mole of this compound. Phosphorus is 30.974 grams per mole. When I do my arithmetic, that comes out to 61.948 grams of phosphorus. For oxygen, there are going to be 4 moles for every PO4, but there are 2 PO4s, so that's a total of 8 moles of oxygen in a mole of magnesium phosphate. Oxygen is 15.999 grams per mole off the periodic table, and this comes out to 127.992 grams. So to find the mass of 1 mole of the whole compound, I add the mass of the magnesium, the phosphorus, and the oxygen, and I get 262.855 grams per mole of magnesium phosphate. Well, what does a mole of a compound really mean? We know a mole of an element means 1 mole of atoms, or 6.022 times 10 to the 23rd atoms. For a compound, a mole means, if it's molecular, 6.022 times 10 to the 23rd molecules. If it's an ionic compound, there really aren't molecules. There's just a ratio in a crystal. So what a mole means there is 6.022 times 10 to the 23rd formula units. Formula units are really just an individual cluster of the smallest ratio of one ion to another that could be in the crystal. So sodium chloride has a formula unit of NaCl. That means 1 sodium to 1 chlorine. In a real crystal, there are going to be millions and millions of sodiums and chlorines, but the ratio is 1 to 1. And if you could take it apart and sort them out into the smallest little unit in that crystal, it would be 1 sodium to 1 chlorine. So that's an example of what's called a formula unit. Sort of like a molecule, but it isn't. Converting between grams and moles, or moles to grams for that matter, works the same as it did for elements. So you can use this device if you'd like to, cover up moles. That if you want to find moles, it tells you what to do, grams divided by molar mass. If you cover up grams, it tells you to find grams, you take moles times molar mass. So let's work out an example. How many moles of water molecules is represented by 36.03 grams of water? Well, my device tells me if I want moles, I'm going to have to take grams divided by molar mass. So I'll take the grams, 36.03 grams, and I'll divide by the molar mass of water. Well, what's that? Water is H2O. So for hydrogen, I have 2 times hydrogen's molar mass, which is 1.008, so 2.016 total. For oxygen, I'll have 1 times 15.999 grams per mole, because that's oxygen's molar mass. So that comes out to just 15.999. When you add these up, you get 18.015 grams for every mole of water. So I'll divide my 36.03 by 18.015 grams per mole. The units I'll get will be moles because the grams cancel. And 36.03 divided by 18.015 is 2.000 to 4 significant figures. You can also use this formula. If you take moles and multiply by Avogadro's number, you'll get the number of molecules for a molecular compound. For an ionic compound, taking moles times Avogadro's number will give you the number of formula units. Here's an example. How many water molecules is represented by 2 moles of water? Well, if I start out with 2.000 moles of water and multiply by Avogadro's number, which tells me I have 6.022 times 10 to the 23rd molecules per 1 mole, this will tell me when I multiply that I have 1.204 times 10 to the 24th molecules of water. Figure this one out. How many oxygen atoms are present in 2 moles of water? 2 moles of water, I just figured out, is 1.204 times 10 to the 24th molecules of water. Every 1 molecule of water has in it 1 atom of O. So I'm just multiplying by 1. There are 1.204 times 10 to the 24th atoms of O. Try this one. Stop the video and figure this one out. You can use a reasoning that's similar to the last example. Again, starting with how many molecules are in 2 moles, it's 1.204 times 10 to the 24th molecules of H2O. But now the ratio here is different. There's 1 molecule of H2O for every 2 atoms of H, because a water molecule consists of an O and 2 H's. So now I'd have to double, and I come up with 2.408 times 10 to the 24th atoms of hydrogen. One more. Stop the video, give this one a try, and I'll bring you an answer in a little bit. Here's your answer. Starting out with 13 grams. I'm going to link a whole bunch of calculations together in a dimensional analysis of CuSO4. I want to ultimately get to atoms of oxygen, so I'm going to multiply by things that'll get me there. I'm going to have to change this into moles before I can do anything, so I'll find the molar mass of copper sulfate. That means 1 copper, 1 sulfur, and 4 oxygens all added together. Copper is 63.546 times 1, plus sulfur 32.064 times 1, plus for the oxygen I'm going to have 4 moles times 15.999 grams for every mole. When I add this all up, I come up with 159.608 grams for every mole of copper sulfate. So I'll put that in here, 159.608, and I want the grams on bottom, and I want the 1 mole on top. So the grams will cancel out. Now I have moles of copper sulfate. Well, every 1 mole of copper sulfate gives me 6.022 times 10 to the 23rd formula units, FUs. Don't get to say FU in school very often. CuSO4 moles are now canceled out. Now, every 1 FU of CuSO4 has in it 4 atoms of O because of the subscript 4. So now, with my formula units knocked out of here, I'm finally where I need to be, atoms of O. Now I just do my arithmetic. I should have 3 significant figures in my answer. It's 1.96 times 10 to the 23rd atoms of oxygen.